The next part of our lesson is on applications of the equilibrium constant. So we've looked at how to determine the law of mass action and then how to calculate K for a reaction. So now we're going to talk about what is the usefulness of this value for K. If you know your K, you can predict the tendency of the reaction to occur. Now, you cannot predict the speed of the reaction. However, that would go back into the kinetics of it, but you can predict whether the reaction has a tendency to occur in the forward direction towards the right. You can also, if you know K, know if a given set of concentrations represents an equilibrium condition or not, if it's already at equilibrium. And then thirdly, the equilibrium position that will be achieved from a given set of initial concentrations. If you know the K, you can predict that. Now, the extent of your reaction is indicated by the magnitude of your equilibrium constant, so how large the equilibrium constant K is. Large values for K, and we need to sort of define what we mean by large. So if your K is greater than 1, that signifies that the reaction is product favored. So you have more products than you do reactants. Think about it. When we calculate K, K is determined by taking the concentrations or the pressures of your products, and then that's divided by the concentrations or the pressures of your reactants. So if you're going to end up with a value greater than 1 for this answer, the quotient, the numerator is going to have to be larger than the denominator. So you'd have product favored if the K ends up being greater than 1. So what this means is when equilibrium is achieved, most of the reactant has been converted to products, so the equilibrium is said to lie far to the right because mostly products exist and the products are on the right-hand side. Small values for K, so when K's are less than 1, that will signify the reaction is reactant favored. So you have more reactants than you do products. So this would occur like with a weak acid equilibrium when we talked about that in chapter 4. When we said like acetic acid would be like 95% would be still reactants, the acetic acid, and only 5% or so would actually be the ions in solution. When you have a K less than 1, what that means is that when equilibrium was achieved, very little of the reactant has actually been converted to product. So the equilibrium is said to lie far to the left because mostly reactants exist and the reactants are on the left side. So let's now talk about the reaction quotient. And thinking in terms of a chemical reaction occurring for some time, we'll call it time equal to T, at some time in the reaction when the system is not at equilibrium, we can determine the reaction quotient, and from the reaction quotient, we can determine the direction the shift will need to take in order to reach equilibrium. So the reaction quotient is actually calculated similarly to how we calculate K. The Q, or reaction quotient, takes the place of the K in your equilibrium constant in the law of mass action. We use Q to determine the direction of shift in our equilibrium. Now, the way that we get Q is we apply the law of mass action to our initial concentrations instead of the equilibrium concentrations. So when we're calculating K, that's the equilibrium constant, and we're plugging in equilibrium concentrations to get that value. We would find Q, the reaction quotient, the same way, except instead of equilibrium concentrations or pressures, you would plug in the initial. So the initial concentration of C raised to the L power times the initial concentration of D raised to the nth power divided by the initial concentration of A to the J times the initial concentration of B raised to the K. Remember, these little zeros at the bottom represent initial concentrations at the very beginning. So in order to determine the direction a system will shift in order to reach equilibrium, what we do is we calculate Q and we then compare Q to K. Remember, Q represents the initial set of conditions and K represents the equilibrium conditions or equilibrium constant. So once you calculate Q and compare it to K, you have three case scenarios that you will run into. If you find that Q is equal to K, that means the system is already at equilibrium and no shift will occur in the reaction. If Q happens to be greater than K, then that means that the system will shift to the left or to the reactants. And what that would achieve is it would consume some of the products and reform some reactants. And it will shift until equilibrium is achieved or established. So if Q is greater than K, the reaction is going to always shift to the left, towards the reactant side. If Q is less than K, the system will shift to the right or to your products, consuming the reactants and forming products. And it will shift until equilibrium is achieved. And at the moment the equilibrium is achieved, that is when your Q would then equal K again. So if Q is less than K, the system shifts to the products or to the right. Now, I have always remembered this. If you think in terms of your reaction, the reactants in equilibrium with your products. And when you are doing this class, you want to compare Q, write Q down first, and then compare it to K. So if Q equals K, it's at equilibrium. If Q is greater than K, I always remember that it shifts towards the direction that this greater than sign is open towards. So it shifts this direction to the Q. It shifts to the side that this is open towards. So in this case, it's open towards the Q side, which is the side the reactants are on. If Q was less than K, it's going to shift to the side that the sign is open towards. It's open towards the K side. So it's going to shift towards the products because the products are on this side. That's just a little way that I've always remembered that without having to think too hard about it. So let's try a couple of examples here. I'm going to just do one of these with you in the video lesson, and we'll do the other two in class. So this problem says at 500 degrees Celsius, K is equal to 6.0 times 10 to the negative 2. So they're giving you the K value. And again, y'all, the units on K are really not important for this. I want you to predict the direction the system will shift in order to reach equilibrium. So notice here they've given you the initial concentrations. So let's write our law of mass action. So if you do it in terms of Q, you'd have concentration of ammonia initial to the second power divided by concentration of nitrogen initial to the first power times concentration of hydrogen initial to the third power. So calculating Q, plug in your ammonia concentration, 1.0 times 10 to the negative 3, and that's going to need to be squared. Nitrogen initial concentration is 1.0. Let me fix that a little bit. That's looking kind of rough. Okay. So again, 1.0 times 10 to the negative 5th, and that's going to be to the first power. And then for the hydrogen, 2.0 times 10